In this video, we're going to introduce the concept of a set. So the term set can mean many things if you're just using the term in a general sense, but it means something very specific in a mathematical context. So we define a set as a collection of objects whose contents can be clearly determined. So we have a collection of items, and we have to know specifically what is and is not contained in this collection. Now, each individual object we're going to refer to as an element. So in general, we're going to use sets to group objects into meaningful categories based on what they have in common. Now, this is not an absolute requirement. You can technically have a collection of any items you want. They don't necessarily have to have something in common, but typically when we use sets in the context of an actual situation, things are being put together in the set because they have something in common, because there's something meaningful that relates the individual items in the set to one another. So we're first going to talk about how we'd represent a set. So in terms of labeling a set, we're typically going to use a capital letter. You can use any capital letter you want. You could just use S for set, but it's not a bad idea to use a meaningful letter. So if your set describes something specific, maybe choose a letter to label your set that has something to do with the contents of the set. So we'll look at an example of that in a minute. Now, in terms of actually representing the contents of the set, we have three different methods for doing this. So number one, we can use a description. In other words, an actual word description of what is in the set. Now, the method we're going to use most often is what we call the roster method. So this is actually listing out the individual items in the set. Now, in order to indicate that we're looking at a set rather than some other type of mathematical structure, we're going to put curly braces around our list. So the curly braces indicate specifically that we're looking at a set. Parentheses, brackets, very similar to braces, but they mean something different. The braces mean we're looking at a set. And then the individual items are going to be separated by commas. Now, when we actually make a list of the contents of a set, the order actually does not matter. So if we're looking at a particular list of items and we rearrange them, if we're talking about a set, the rearrangement doesn't actually make a difference. So any particular collection of items where we have the same contents, regardless of order, is going to be the same set. Now, something we call maybe a list, the order does matter. We put the items in a particular order, and if we rearrange them, it would make a difference. If we're specifically talking about what we're referring to as a set, the order we list the contents in is not going to matter. Now, our third method for representing a set is going to kind of be a hybrid of the first two. It's what we call Setbuilder notation. So it's going to look like this in general in structure. The way we would read this is all x such that. So the vertical line we read as such that. So all x such that, and then the line is going to be followed by conditions on our variable that qualify it to end up in our set. So we're going to think of the x as just a general variable representing a general element in the set. What we want to know is what sort of qualifications would x have to meet in order to represent something that would be contained in this set. And that's what this condition over here is going to determine. It says that's what it's going to tell us. So the condition can take on a variety of forms. We could write a condition in words. In other words, x is blah, 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 something in words. Sometimes we'll have something like an equation or an inequality that describes the values that x could take on, but this can look a variety of different forms. And then notice we have the curly braces around that. That again indicates that we're talking about a set versus some other type of structure. So let's look at an example and let's talk about representing the set. So we're going to let C be the set of all US coins with a value less than $1. So this is an example of the description of a set. So we have the set that we're calling C, and the description of this set is that C contains all US coins that have a value less than $1. So based on this description, we know exactly what is in this set, and we know exactly what is not in this set. The only things in this set are going to be coins, US coins, that have a value less than $1. Now we want to take this description, which again is one method for representing the contents of this set, and we want to write it in roster method and then in Setbuilder notation. So in roster method, we're just going to make a list of the individual items in the set. Now again, the order we list them in does not actually matter, But when we're talking about some type of collection of items that have something in common, in a lot of situations, there's going to be sort of an obvious order, a meaningful order. It's not a bad idea, if you can think of a meaningful order, to list the contents of the set in that particular order. So if we're talking about something like coins, one particular order that might be meaningful is in terms of value, from lowest value to highest value, or vice versa. So if we were going to list the contents of this set from lowest value to highest value, then the individual items in this set are going to be a penny, a nickel, a dime, a quarter, and then this one's not as common, but technically we also have a coin in the United States called a $50, so it's worth 50 cents. You don't see them very often, but occasionally you will see one. So that's going to be the roster method version of representing this set. And again, if we had all of these same items just in a different order, it's still a valid representation for the set, and it's still the same set. Now in set builder notation, again, it's kind of a hybrid of the description and roster method. So we're going to use our curly braces again. We're going to define a general variable. Typically we just use X, but you can use anything you want. So all X such that, and then we have a condition on X. So in this case, our condition is that X has to be a US coin worth less than $1. So notice typically when we use a variable in mathematics, typically the variable is going to take on some type of numerical value. That is not necessarily a requirement. Variable just means unknown. It means it could take on different forms, different values, depending on what it's representing. In this case, it's representing US coins. So the US coin we've represented in words. So this particular variable, as long as it meets this requirement, could take on any of these 5 values. And so that's going to be our representation in Setbuilder. Now, specifically the roster method is what we're going to focus on for the most part. So roster method is going to be the most valuable method we use to represent a set because it's going to show us the actual individual contents of the set. So in a lot of situations, particularly in situations where we want to count how many items are in the set, actually being able to see the individual elements, the actual contents of the set, is going to be important. Now, one thing we have to keep in mind though, if we're going to make a list of the items in the set, we have to keep in mind that some lists are going to be very, very long, and some lists may actually be impossible to write out completely in roster method. So for instance, if we're talking about the set of all real numbers, that just literally means all the numbers from negative infinity to infinity. In other words, if you looked at a number line all the way from the left, all the way over to the right, any number anywhere on that number line would be considered a part of the set of all real numbers. Well, there's obviously no way we can make a list of all the numbers that would be in that set. There's infinitely many. So you could start writing numbers, you could write them for the rest of your life, and you'd still never be able to write the whole list. So how do you actually use roster method if you can't make a full list of the items in the set? What we're going to do is we're going to use roster method in general in terms of making a list, but rather than actually listing out every item, we're going to abbreviate the list. So the idea is we want to list enough of the items in the set to establish a pattern. The pattern then is continued by writing an ellipsis, which is the 3 dots. So when we write an ellipsis, we essentially mean continuing in the same fashion. So if we can establish a pattern with some of the elements, then the ellipsis just says follow the pattern and continue indefinitely. Now this can take, again, a couple of different forms. So suppose we have a long set, but one that does actually terminate. Well, how we use the ellipsis is going to be different than how we use it in a set that is infinitely long and doesn't terminate. So let's look at an example and then I'll show you how it will work both ways. So for example, let's let S be the set of all US state postal abbreviations. So in this case, we can think of S as maybe representing state. So that's why that would be a meaningful label. We want to express this set using the roster method. In other words, we want to make a list of all the individual items that would be in this set. Now, if we're just talking about actual US states, not US territories, how many items would be in this set? Well, there would be 50 items in this set. So it is a finite set. We could actually list out 50 individual items, but it would be very tedious to do so. So rather than actually making the full list where we have every single individual 50 of those 50 items written out, we can use this ellipsis notation to abbreviate the roster method list. So what we need to do is we need to write enough of the contents of the set to establish the pattern so that anyone looking at this list would understand what this list represents and would understand the pattern. So if we're talking about state postal abbreviations, how would we establish a pattern for something like this? Well, again, think in terms of order. Order does not technically matter, but if we're talking about establishing a pattern, ideally we want to find some type of meaningful order so that if someone were to look at this set, they understand based on the ordering what the pattern is that we've established. So if we're talking about something like postal abbreviations, one particular ordering that we might use would be an alphabetical order from A to Z. So we could either list it alphabetical by abbreviation, or we can think of the order that the states come in alphabetically. So if we're going to think in terms of states, the first one that we have is Alabama. So it's Alabama, Alaska, Arizona, Arkansas, California, Colorado, so on and so forth. Now, in order to establish a pattern, the general rule is you want to have at least 3 things listed out. 3 things is typically enough to establish a pattern. 2 is usually not. So if we're going to list out the first 3 states abbreviations, Alabama, Alaska, Arizona, that's going to be AL for Alabama, AK for Alaska, and then AZ for Arizona. Once we have these 3 elements listed, we've established the pattern for the contents of this set. So after we list the 3rd element, we can use the ellipsis symbol to just indicate that the pattern continues in that same fashion. Now, what we do after the ellipsis depends on the type of set we're looking at. So we decided this set does terminate. There's 50 items in the set. Again, we could make the actual list, but we're using this abbreviation technique. But we do know that this particular set ends somewhere. In this case, the last state alphabetically is the state Wyoming. So in order to indicate that this set does in fact have an end, it has a point where it stops, we don't just leave the ellipsis and close the braces. We have to actually indicate where this set stops. So in this case, if the set stops with Wyoming, we're going to list the postal abbreviation for that, which is WY, and then we'll close the curly braces. So this indicates that based on this pattern, this would be the last element in the list. And then based on the fact that we have a last element, that tells us that this set does in fact end. It's finite in length. Now again, if we're talking about a set that's infinitely long, where we don't actually have somewhere where it ends, something that goes off to infinity or negative infinity, something like that, rather than writing a final element, because there is no final element, we'll just draw the ellipsis and then we'll close the braces. So if you see the ellipsis and then the braces close, that means the set is going to continue on indefinitely. The pattern has been established and then the set continues indefinitely. If you have an actual element listed before the braces close, then that means the set is finite. That means there is a final element. It means the set actually terminates. So we're going to use different combinations of these notations in different situations. But again, in a sense, roster method is going to be the most important one because it's the most literal representation of the set. It shows us the actual contents of the set, and so it's going to in some ways be the most useful representation. So I want to talk about a specific set that's going to seem probably silly, a little bit useless at first, but it is going to be meaningful for the additional things we're going to use sets for. So the specific set we want to talk about is what we call the empty set. So the empty set is a set that contains no elements. So it's a set, but it's a set that doesn't have anything in it. Now we have 2 notations for saying we're looking at the empty set. So the first notation is going to be an O with a diagonal slash through it. And then the second notation is just going to be curly braces with nothing inside the braces. So you may have used the empty set before, you may have used these notations before if you've taken an algebra class and you've looked at equations that have no solution. So sometimes rather than writing no solution for an equation, you'll indicate that the solution set is the empty set. In other words, if you were to try to make a list of the solutions, because that equation doesn't have any, that particular set is going to be empty, hence the empty set. Now, knowing whether or not something is empty is going to be important. Sometimes we may have something that is empty, but it doesn't immediately look empty in the sense that we're using the empty set notation. So we can have a set whose contents are described, but it's actually an empty set based on how the contents are described. So let's look at a couple examples here. So we have some different sets. We want to know, does this represent the empty set or not? Does it actually have some contents or is it empty? Okay, so first one, all x such that x is a number less than 4 and greater than 10. Okay, now the word and, we have to pay attention to that. And means both at the same time. So condition 1 and condition 2 have to be true at the same time. So the only values of x that would be included in this set are values where the number is also less than 4 and greater than 10 at the same time. Well, what values of x are both less than 4 and greater than 10 at the same time? There aren't actually any numbers that would fit both of these qualifications at the same time. So even though we haven't written the empty set here, this set is actually the empty set. It's the same as the empty set. This set doesn't actually have any contents because there aren't any values of this variable that would meet all the qualifications in order to be contained in this set. So that set would be empty. Now what about the next one? What's the only thing that's changed? So all x such that x is a number less than 4 or greater than 10. So the only thing that changed is an and became an or. Now when we talk about or mathematically, or means something very specific. It means one or the other and possibly both. That's the distinction. Sometimes or just means one or the other. Our or means one or the other and possibly both at the same time. So in order for something to be contained in this set, it only has to meet one of the qualifications. If it meets both, that's fine, but it only has to meet one or the other in order to be considered something that would be in this set. So our first qualification, it has to be a number less than 4, or second qualification, it has to be greater than 10. Now we know there aren't any numbers that meet both qualifications at the same time, but are there numbers that meet the first qualification by itself? And are there numbers that meet the second qualification by itself? Of course, in this case, the answer would be yes. There are numbers that are less than 4. There are numbers that are greater than 10. So any number that would meet one of those qualifications would be a number contained in this set. So this is a non-empty set. This set does actually have contents. It does actually contain elements. Now what about the next one? This is in roster method. We have the actual list. It's a list and the list is 0. So is this the empty set? 0 kind of means empty. It means nothing from a numerical standpoint. It means neither positive nor negative. But from the standpoint of being a set, is this set empty or is it non-empty? Well, in this case, this set is non-empty. 0 is an object that is contained in this set. So this is a set containing the element 0. It's a set with one element in it, so it is non-empty. So even though 0, we think of 0 as kind of representing nothing, if you think of 0 as just an item in the set, that particular set contains the item 0. It has contents, so it is non-empty. Now this last one we're going to have to be really careful with. We have the curly braces, and then inside the curly braces we have the symbol for the empty set, the O with the slash through it. Is this set empty or is it non-empty? Well, as it turns out, this one is also non-empty. The empty set is an item contained within the bigger set. So if we think of these curly braces as enclosing items in the set, well, that particular set has one item inside of it. It has the empty set inside of it. That's the contents for this set. So even though we're talking about something containing the empty set, the set itself in question is non-empty because it does have contents. So the big takeaway from this one, more than anything, is do not mix notations. If you mix these two notations and put them together, you will have something that no longer represents the empty set. So you're either going to use the O with the slash through it, or you're going to use the curly braces, but you don't want to use both at the same time if you're trying to indicate that something is empty. So why would we talk about something that's empty, something kind of like 0 from a set standpoint? We're going to talk about the empty set in terms of comparison. So if you're comparing two sets together, and specifically you're interested in what they have in common. If you're talking about a set or a pair of sets where they don't have anything in common, then we can think of that particular set of what's in common as the empty set. So the empty set is going to represent those situations where we're comparing two things and then those two things don't have anything in common. Now, suppose something is not empty. We have a set that's non-empty. How do we describe things that are in the set in terms of set membership, in terms of individual elements and whether or not they're in the set? So our notation for set membership is going to be this symbol. This is the Greek letter epsilon. This is a lowercase epsilon. So this symbol is going to be used to indicate that some object is an element of the set. So the way you'll see it written is to the left of the symbol, you'll have the particular element, the particular item in the set, and then to the right of the symbol, you'll have the set itself. So you either may have the label, the capital letter representing the set, or you could have the set itself. You could have something in roster method, you could have something in Setbuilder notation. This is a pretty flexible notation. It can look a variety of different ways. Now, what if we want to say that something is not in the set? Anytime we take a symbol and put a slash through it, that's essentially the same thing as introducing the word not. So if this symbol means is an element, this symbol means is not an element of the set. So again, if we put a particular item to the left and then put the set to the right, that statement would be saying this element is not an element of the particular set in question. So let's look at a few statements involving these symbols, and we want to determine whether each of these is true or false. So first statement, R is an element of this particular set described in roster method. Is that true? Is that false? Well, we have to think about what that set represents. Notice that set is in roster method, but we haven't actually listed out every element in the set. We have that ellipsis, which indicates that we've established a pattern, and then we want to continue the pattern. Well, what's the pattern here? What are the contents for this set? We have lowercase letters all the way from A to Z. So it's lowercase letters listed in alphabetical order. Would R be contained in that set? Well, the answer would be yes. So this particular statement with this particular symbol is true. That would be a true statement. Now, next one. 7 is not an element of this set. Now again, we have something in roster method, but notice we don't have an ellipsis. In other words, these are all the contents of that set listed. Those are the only things in that set. So 7 is not an element of that set. In this case, that's also going to be true. If we look at this set over here, there is no 7 listed, so 7 is not an element of that set. That is a true statement. Okay, A is an element of this set. Well, that one's easy. It's essentially matching. You can see it, so that one's going to be true. Now let's change that last one slightly. I want to focus on notation here, and I want to make a distinction between what is and is not proper notation. The set containing A, an actual set, is an element of this set, the set containing A and B. As it turns out, this statement is actually false. So the previous statement is true, but this statement is false. It is not a true statement. Here's why. The set containing A, if we think of that as its own element, that as its own element cannot be found over here in this particular set. This is a set containing the element A and the element B. Well, this, if we think of this as an element, the element itself is the set containing A. So the only way this statement would be true is if the set we had on the right-hand side actually contained sets within it. So if instead of being A and B, we had the set containing A and the set containing B, in other words, we had nested curly braces. We had curly braces inside of the curly braces. Then we could potentially have a true statement. But in this case, this is not the proper symbol to indicate the relationship between these two things. So this one's true, this one's false. Now you're probably looking at that statement and saying, well, they do have a relationship. There should be a way of relating those two things. This set and this set should have something in common. Well, the answer is yes, they do, but they're not related using this epsilon symbol. They're going to be related in a different way. So this particular set, this smaller set containing A versus this larger set containing A and B, this is actually what we're going to call a subset. So it's a set contained within another set. It's a set whose contents are contained in the bigger set's contents. So we'll actually talk about that in the next section, the concept of a subset. Keep in mind, if you look at this and you feel like there's something there, yes, there is something there, but not based on the notation we have. So when you see this symbol epsilon or not epsilon, you have to think very literally. So imagine you didn't know what letters represented, you didn't know what numbers represented, they just looked like symbols. You're looking for that actual symbol and in the contents of the set that that's in question. You're looking in relation to this particular set. So if you can literally see that symbol copied and pasted into the set in question, then you can say that's an element of the set. In order for this to be true, again, this whole element, imagine copy and paste into the next set. If that's true, if you can find it like that, then set containment is there. If it's not, then that's not an element of the set. Now, case in point, this next one. R is not an element of this set. Is that true or false? Well, you might look at that and think initially that's false. R is contained, so saying it's not contained would be a false statement. But as it turns out, this is actually a true statement. Why is it true? Well, think about what the pattern is for the actual set. It's our letters from A to Z in alphabetical order, but notice it's all capital letters. It's capital A, capital B, capital C, all the way down to capital Z. This is a lowercase letter. So a lowercase letter is not going to be contained in a set of uppercase letters. And again, that's a situation where you kind of have to take yourself out of the context of what the actual elements represent. If you were to look at this individual item, can you find that individual item exactly as written in the set in question? And if the answer is no, then that means that's not an element. So R is not an element of this set. That is actually going to be a true statement. Okay, Monday is an element of, we have a set and Setbuilder notation. So all X such that X is a day of the week. So we've described what's in this set. We don't have an actual list, we don't have roster method, but we have a way of understanding what is in this set. So anything in this set is something that is a day of the week. Well, is Monday a day of the week? Of course, the answer is yes. So Monday is an element of this set based on the description we have of the contents of that set. Now, what about the next one? The set containing Monday is an element of this set. And notice it's going to be the same set as previously described. Well, this is false, just like this particular statement was false. The set containing Monday is not an element of this particular set. Again, you have to think in terms of copy and paste. The whole set as its element, as its own element, is contained in this particular set, yes or no? Well, the answer then again would be no. We don't have sets within sets in this case. This is its own set with individual elements. In order for this statement to be true, this set would have to contain individual sets inside of it. That would be the only way that this statement would be true. And so in this case, it's false. But again, just based on the relationship here, we could think of this as what we'll call a subset of the larger set. It's a set whose contents are contained within the other set. Okay, so again, we'll develop that notation a little bit later. We'll talk about that in the next section. Now, a specific set we're going to use a lot is what we call the set of natural numbers. So rather than just looking at all numbers as a blanket statement, which is sometimes difficult to talk about, if we look at all real numbers, that's infinitely many numbers. If we look at any two integers, say 0 to 1, well, there's infinitely many numbers between them. So if we're talking about real numbers, we're talking about a really, really big set. For most of the things we're going to do, we're going to focus on counting type numbers. So we call these the natural numbers. So the set of natural numbers is going to have all of our counting numbers starting with 1. So 0 is not considered to be a natural number. So counting numbers, and then when we want to represent it in writing, or in type, if we're going to type it, it's going to be a bold-faced capital N. That's going to be the way we type it. So you type a capital N, you bold it. Now, if you're handwriting it, you don't bold things when you handwrite. This is actually going to be the symbol if you're going to handwrite it. So you're going to draw your capital N, and then to the left of the N, you're going to draw a little vertical line. So it almost looks like you're thickening up that particular line where you start writing the N. Looks kind of like you wrote IN, but you're going to put it so close together that that vertical line is essentially going to be part of the N. So this would be the natural numbers defined in roster method. We have all of our counting numbers starting at 1. So 1, 2, 3, 4, ... Now notice with this ellipsis, there's nothing after it. That's because this is an infinitely long set. We're only talking about counting numbers, but we can keep counting indefinitely. We'll never be able to stop counting. It goes all the way out to infinity. So you might be thinking, well, why didn't you put infinity at the end and then close the braces if that's where the set ends? Well, we have to keep in mind infinity is not really a number. This set does not actually end. Infinity just means continuing forever. But there's no way you can actually count to the number infinity. So the only things you'll be able to write in a set in terms of numbers that you can count are going to be actual numbers you can count. So anything related to infinity or negative infinity, those are not actual numbers that we can count to, so we can't necessarily write those in terms of an element in a set. That ellipsis is just going to indicate it continues in this fashion and goes on to infinity. So we'll be interested in the natural numbers as a whole, but also in individual collections, smaller sets of natural numbers. So based on some of these descriptions, some of these different representations, let's make a list of all the numbers that would be included in these sets in roster method. Okay, so set A is the set of natural numbers less than 5. Okay, now we're going to have to be careful with the wording. So the natural numbers less than 5. Notice it doesn't say 5 or less. It says strictly less than 5. What that means is that 5 is not going to be included in this set. Only numbers that are strictly less than 5 are going to be contained in this set. Now, does that mean you have all numbers less than 5? Well, the answer there is no, because we're only looking at natural numbers. So we're limited to the numbers that are already in this set. We're starting with the numbers in this set, and then we're imposing an additional restriction on them. We're saying we only want to keep the numbers that are less than 5. So if we're looking at natural numbers that are also less than 5, that's going to be the numbers 1, 2, 3, and 4. Those are the natural numbers that are less than 5. Now, set B is the set of natural numbers greater than or equal to 25. Notice how the wording changed, less than versus greater than or equal to. That equal to part tells me that my boundary number, we can actually have that boundary number as part of the set. So we're looking at natural numbers to start with, but we want our numbers to be greater than or equal to 25. So now we're increasing. We're starting with a lower number and we're increasing from there. The boundary is the lower number. Here the boundary was an upper number. Here the boundary is a lower number. So in terms of our natural numbers, we're starting at 25, so equal to 25, and then we want the numbers that are greater than that are also natural numbers. So 25, 26, 27, and then I put the ellipsis. Now, why do I put the ellipsis here? Remember, this particular set is going to continue forever, because the natural numbers continue forever. So if we're looking at natural numbers greater than or equal to 25, there is a distinct place where this set starts, but there is no place where this set ends. So that ellipsis is going to indicate we've established the pattern and we're looking at the successive numbers that follow that pattern, and in this case the pattern never ends. Now, instead of a description, let's look at set builder notation. So C is going to be the set of all x such that x is an element of the natural numbers. Okay, so we're using that notation again. There's that epsilon. X is an element of the natural numbers and x is even. So two requirements for something to be in this set. Number one, it has to be in the set of natural numbers. And number two, it has to be even. In other words, it has to be a multiple of 2. So we're restricted to the set of natural numbers, and then we're imposing that further restriction that we're only looking at even values. So low to high, that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18. You get the idea. Again, once we have 3 elements, we can establish a pattern. And then we have the ellipsis to indicate continuing in the same fashion. And again, this set doesn't terminate either, so we indicate that by just closing the curly braces. Okay, the set D is all x such that x is an element of the natural numbers and x is less than or equal to 100. Okay, so it's a natural number. It's contained in the set of natural numbers. We're only looking at those kind of numbers to start with. And also, the number is less than or equal to 100. Now that means 100 is going to be included. So we want numbers that are smaller than 100, and we're also going to include 100 itself. Now again, does that mean we're going to look at all the numbers less than 100? The answer is no. Remember, we're only looking at natural numbers. So x has to be a natural number, and it has to be smaller than or equal to 100. So we're only looking at numbers that are already in this set. So we'd start at 1. 1 is less than 100, and then 2, and then 3. Maybe we could make the whole list. Surely it is a finite list. We're only looking at the numbers from 1 to 100. But if we don't want to make the list, again, we can use the ellipsis notation. So we establish the counting pattern, 1, 2, 3, and then we have our ellipsis to indicate that we continue in the same fashion. This set terminates. This is not an infinitely long set. This set does not go off to infinity, so we'll write the last element in the set, which is going to be 100, and then we close our braces. Now you're going to have to be very, very careful with this inequality notation. Having the equal to versus not having the equal to is going to be very important. So let's look at the next one where we actually have 2 contained in the same set. So the set E is all x such that x is an element of the natural numbers and 70 is less than or equal to x, and then x is also less than 100. So this is what we call a compound inequality. It's actually 2 inequalities in one. So it's expressing a relationship between x, 70, and 100. You can think of x as being between these numbers. We write it between them, so it is between them in terms of counting order. So x has to be something bigger than 70 or possibly equal to 70. Notice we've got that equal to. So it's bigger than or equal to 70, but it's also less than 100. Now, does that mean it can be equal to 100? No, it cannot be equal to 100. It's strictly less than 100. So if we're talking about counting numbers, we're starting at 70. 70 is our lower boundary. That's the smallest number we can have. But what's our upper boundary? It's not actually 100. We don't actually have 100 as an element in this set. We can only be strictly less than 100. Well, if we're talking about natural numbers, what's going to be the highest number we can get to that's still going to be less than 100? Well, of course, it's going to be 99. So this particular set is going to go from 70, our lower boundary, all the way up to 99, our upper boundary. And again, this is a finite set. We could technically make a list of everything that's in that set, but if we don't want to, we can use the ellipsis notation. Now, I don't want you to use the ellipsis notation too liberally. If you have maybe 10 to 15 elements in a set, take the time to make the list. You want to use the list when it's a large list, something where you don't necessarily need to see all the contents, and where taking the time to write the contents would just be unwieldy. It would be just ineffective, and it would be a waste of time to do something like that. But don't look at this notation and think, oh, this is going to save me a bunch of time. I'm going to use this all the time. You're not going to use it all the time. You're only going to use it when your sets start to get large. But in a lot of situations, seeing every individual item in the set is going to be important. It's going to be helpful. So when in doubt, if you can make the list, if it's realistic to make the list, it's not a bad idea to just take the time and make the list. Okay. So what happens when we're looking at two sets? That's essentially what we're going to do using sets. That's why we're developing all of this, in order to talk about multiple sets, things they have in common, things they don't have in common. We're going to start small though. So we're going to talk about this term called cardinality. Cardinality means something very specific. And then the idea of two sets being equivalent, and the idea of two sets being equal. The words equivalent and equal almost mean the same thing if we just use them in general. So if you're just using those terms in conversation, you use them and they probably mean essentially the same thing to you. Just like the term set means something very specific in mathematics, the terms equivalent and equal also mean very specific things, and they don't mean the same thing. So saying that two things are equivalent and saying that two things are equal is very different. Now let's start with this term cardinality. So cardinality, another way of saying that is cardinal number. We're identifying a specific number associated with a set. So the cardinal number of a set A, our notation for this is going to be n of A. That's how we read that. So lowercase n, and then we're going to put the sets label in parentheses, n of A. This is defined as the number of distinct, in other words, different, unique, non-repeated elements in our set. So essentially, it's the count of how many things are in the set. So for instance, the first set we have up here, the set A, its cardinal number would be 4 because we have 1, 2, 3, 4 elements in the set. Now, I did say distinct, different. We do have to make a distinction there. Duplicating elements doesn't change the cardinal number. So suppose you have a set where you've listed an element multiple times. Say it's the set and it just contains a bunch of ones. Maybe there's 100 ones in the set. Well, as it turns out, the cardinal number for that set is only 1. There's 100 things in the set, but they're all duplicates of the original. Anytime you have duplicates, you only count them one time. So duplicating elements is not going to change your cardinal number. You're only going to count the duplicates one time. So we're looking for the number of unique, the number of different elements in the set. So let's look at a few sets in terms of calculating our cardinality. So if the set X is equal to, in roster method, 1, 2, 3, and the set Y in roster method is 1, 1, 2, 2, 3, 3, then what are the cardinal numbers of these sets? Well, let's start with X, n of X. We have three unique elements in here, so the cardinal element is going to be 3. Now what about Y? Y technically has 6 elements in it, but when we're talking specifically about the cardinal number, we're talking about the number of different elements. We're not considering duplicates. Well, if we're talking about different elements, then this set still only has 3 elements. Each of those 3 elements has been duplicated once, which then gave us the 6 in total. So the cardinal number for Y is also going to be 3. So notice that even though these two sets looked different in terms of size, their cardinal numbers are the same. Typically, we don't want to list duplicates. If you're going to use sets, for instance, to talk about solutions to an equation, something like that, there are some equations where we get duplicated solutions. We don't list them more than once. The general rule with sets, if you're going to use a set and create one yourself, is you don't typically list duplicates. You can have situations where there are duplicates listed, for instance, like this, But if you're going to write a set yourself in the context of a problem, you typically only want to write something one time. Even if it is duplicated in the context of your problem, you typically only want to include it one time in the set, just based on this issue of cardinality and the fact that we don't really consider repeats. Now let's look at a few more. The set A is this set in roster method. Well, remember, this is not the empty set. We looked at this particular one couple pages ago when we were talking about the empty set. This is not the empty set. This set has contents. So we're asking the question, how many elements are in that set? Well, the element in the set is 0, but we're just counting. We're counting how many elements are in the set. So in this case, there's 1 element in the set, so the cardinal number of A is going to be 1. Now the next one, notice it's given in Setbuilder notation. Setbuilder notation is going to be hard to use when we're talking about things like counting, when we're talking about the cardinal number. So this is a good time to convert to a different notation. So I mentioned at the beginning, roster method, that's going to be our most useful technique for writing a set because it truly shows us the contents of the set. This is a situation where knowing the actual individual items in the set is going to be important. So the set B is all x such that x is an element of the natural numbers, so 1, 2, 3, 4, 5, 6, so on and so forth, and x is greater than 12, but it's also less than or equal to 23. So it's between 12 and 23, not equal to 12, but equal to 23. Well, if it's bigger than 12 and it can't be equal to it, where does it have to start? Well, if we're talking about counting numbers, we know it's going to start at 13. And then it's also less than or equal to 23. That equal to tells us we can actually end at 23. So it's not a bad idea to actually take a moment and write out the actual contents of this set. So this set is going to start at 13, and then it goes based on our natural numbers, so 1 at a time, all the way up to 23, and that's where it terminates. Now this is a set we could write with the ellipsis, or we could write everything out. The benefit of writing everything out is then you can literally just count how many elements are in the set. Here's the risk of not counting. Or not writing everything out, I should say. You might look at these elements and think, well, the highest one is 23, the lowest one is 13. If I subtract them, that's going to tell me how many sets are in the middle. That's not quite the case. If you take 23 and subtract 13, what do you get? You get 10. But how many elements are really in this set? I'm going to count on my fingers, which seems silly, but it's going to keep us from making a mistake. So starting at 13, we have 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, so that takes us to 10. And then we also have 23, which takes us to 11. So if you were to just subtract higher minus lower, it looks like there's 10 elements in the set. There's not. There's 11 elements in the set. So being able to write out everything in this set is going to allow you to count a little bit more carefully. Even the difference of one element can make a difference in the end. Now, what about this set? What is this? Remember, that's the empty set. How much is in the empty set? How many elements are in the empty set? Well, the empty set doesn't actually have anything in it. Remember, it's empty. There are no contents. This is not the empty set. This is the empty set. Well, if the empty set doesn't have anything in it, then its cardinal number is going to be 0. This is actually another definition for the empty set. We can also think of it as the set whose cardinal number is 0. So any set whose cardinal number is 0, any set that contains 0 elements, is going to be the same thing as the empty set. So when we say the same thing, when I use that particular terminology, what does that mean? Well, remember, equivalence, equality, those are the two words we're going to use. They don't actually mean the same thing from a mathematical standpoint. So we're going to start with equivalence. Equivalence is less strict. Equality is stricter. So two sets are said to be equivalent if the cardinal number of one is equal to the cardinal number of the other. In other words, if they have the same number of elements, then we consider them to be equivalent. We're not actually paying attention to the exact contents, to what's actually in the set. We're just looking at how many items are in the set. And again, keep in mind this issue of repetition. In terms of the cardinal number, we only count elements once. Even if we see it more than one time, we only count it the one time. So we're looking at our two sets, we're comparing their contents. We want to know, do they have the same number of elements? If they do, they're equivalent. If one has more than the other, they're not equivalent. Now, two sets are said to be equal if they contain exactly the same elements, regardless of order or repetition. So one thing to keep in mind is you can't have sets that are equal without them already being equivalent. In order for them to contain the same elements, they have to be the same size by default. Think about it. Try to think of a counterexample. Could you have two sets that have the same elements and they don't have the same number of items? Well, it doesn't make any sense. If we're talking about having the same elements, we should be able to take an element in one and exactly match it to the element in the other for every single element. So if we're going to pair them off from set to set, we should have the same number of items in the set. So it has to be the same items, and by default, it's going to have to be the same number of items. Now, order and repetition are not going to matter. We can rearrange the contents of the set. It doesn't change the set. And again, in terms of the cardinal number, repeating elements doesn't make a difference. So repeating numbers, we only count them one time. So we can have a set that looks bigger than the other, but as long as they have the same contents, regardless of order or repetition, we'll say that the sets are equal. So we can be equivalent without being equal, but we can't be equal without being equivalent. So equivalent is less strict, equal is more strict. In order to be equal, we have to already be able to say that our two sets are equivalent. So let's look at some pairs of sets. So here's our first pair. A is 489, B is 894. So first question, are these sets equivalent? In other words, do they have the same number of distinct elements? Well, the set A has 3 different elements. The set B also has 3 different elements. So their cardinal numbers are the same, so they are equivalent. Now, are they equal? They're already equivalent, so we're halfway there, but we have to make sure that the contents are exactly the same. In other words, every element in A matches up to an element in B. Well, we have a 4, we have an 8, and we have a 9. So even though B has been rearranged, the contents of these two sets are exactly the same, so these sets are also equal. So same size and same contents. Now what about the next pair? So A hasn't changed, but we've changed B. So A is 489 and now B is 895. Are these sets equivalent? Yes, same cardinal number, 3 elements, 3 unique elements in each of them, so they are equivalent. But are they equal? Here the answer is no. If we look at the element 4, we can't match up the 4 in A to something in B. So as soon as we find one element that doesn't match, automatically that means the two sets cannot be equal. We can't match all the contents, so we can stop at that point. We can say they're not equal. Now what about the next two? So A is 135, B is 0, 135. Are they equivalent? Well, you might look at 0 and think, well, 0 is nothing. 0 doesn't count. Not quite. 0 is a number. It is an element. It is a thing in this set. So how many unique items does A have? Well, 1, 3, 5, those are all different. So the cardinal number of A is going to be 3. And then the set B has 0, 1, 3, 5. It has 4 unique elements. So its cardinal number is 4. So a cardinal number of 3, a cardinal number of 4. These two sets have different numbers of items, so they are not equivalent. Now, if your sets are not equivalent, automatically you can say they're not equal. Equivalence is required for equality. So if they're not equivalent, they can't be equal. It can go the other way, but it can't go that way. Okay, one more. This one is a little bit tricky. We're going to have to be careful. So A is 0, 2, 4, 6, and B is 2, 2, 0, 6, 4. Okay, are they equivalent? Well, if you just look at them and compare the sizes just looking at it, immediately it seems like they wouldn't be, right? Because we have 4 things in A, we have 5 things in B. You have to think about what the cardinal number means. Remember, we're talking about the number of distinct, the number of different elements. So in A, all 4 elements are different. 0, 2, 4, 6, those are all different. So the cardinal number of A is going to be 4. Now for B, we do have 5 elements, But notice that that element 2 is repeated. So if we're talking about the cardinal number, we're only going to count that 2 one time. So in terms of the number of different elements, we have 2, we have 0, 6, and 4. So our cardinal number is going to be 4. So cardinal number of A is 4, cardinal number of B is 4. These are equivalent sets. Are they equal? In other words, do they also contain the same contents? Well, 0 matches up with 0, 2 matches up with 2. We actually get to match it up twice. 4 matches with 4, and 6 matches with 6. So we have the same contents regardless of order. They've been rearranged. That does not matter. Regardless of repetition, the 2 has been repeated. Does not matter. We only look at it the one time. Based on those 2 stipulations, these 2 sets are equal. Exact same contents, exact same cardinal number. Okay, let's look at a couple more, but let's take it up a notch. What happens when you don't actually see things listed out? What if we're in Setbuilder notation? Now again, in Setbuilder notation, we need to be really careful. It's not a waste of your time to take the set and then rewrite it in roster methods so that you can see the actual contents of the set. Particularly in a situation like this, where not only we're comparing how many items are in the set, but we're comparing the actual items themselves. It's a valuable exercise to actually write out the contents of the set. So A is all x such that x is a natural number and x is greater than or equal to 6 and also less than 10. And then B is all x such that x is a natural number and x is greater than 9 and less than or equal to 13. So let's start by actually writing out the contents of these sets. If we want to compare how many items are in each set, again, we kind of have to be careful. We need to know how many items are in there, but we need to be able to see the items in order to get an accurate count. So for A, we're between 6 and 10, equal to 6, but not equal to 10. So natural numbers from 6 to strictly less than 10, that's going to be 6, 7, 8, and 9. So that means the cardinal number of A is going to be 4. We have 4 elements in the set A. Now B is the natural numbers from 9 to 13, strictly greater than 9, but possibly equal to 13. So strictly greater than 9 means we're starting at 10. So 10, 11, 12, and equal to 13, so we have 13. So the cardinal number of B is also going to be 4. So our cardinal numbers are the same, so by definition, our sets are equivalent. Are they equal? Do they have the same contents? Well, that one's pretty easy to spot. They don't actually have any elements in common. The term for that is disjoint. These 2 sets are disjoint. They don't have anything in common, so they are definitely not equal. Nothing in common means they're definitely not equal. So the term is disjoint. Here's sort of an extension to help you think about why we have defined this thing called the empty set. What we're eventually going to look at is what we call the intersection of these 2 sets. So intersection means exactly what you think it means. It means where things intersect. It means where they overlap. These sets don't have anything in common, so they don't actually overlap. So if we were to define a set representing all of the elements that overlap, if there are none, then we can think of that overlapping set as being the empty set. That is why we define the empty set. The empty set means either there's no solution to a situation, or if we're looking at things that 2 sets have in common, those 2 sets don't have anything in common. And again, the word for that is disjoint. That's the word we'll use for that. Okay, 2 more. So A is all x such that x is a natural number and x is greater than or equal to 100 and also less than or equal to 105. And then B is all x such that x is a natural number and x is greater than 99 and less than 106. Something interesting is going to happen here, but it's hard to spot unless we actually write these sets out. What are their actual individual contents? So for A, we're looking at our natural numbers, and we want to be no smaller than 100 and no bigger than 105. But we can be equal to 100, we can be equal to 105. So that's going to be 100, 101, 102, 103, 104, and then the set terminates at 105. That's our upper limit. Now for B, we're between 99 and and 106, but notice that we can't be equal to either of them. So we're looking at natural numbers strictly between 99 and 106. Well, if it's a natural number, the next natural number after 99 is going to be 100. The next natural number that's before 106, that's smaller than that, is going to be 105. So we're looking at everything from 100 to 105 in terms of our counting numbers. Look at these two sets. At that point, definitely the same number of distinct items, so they're equivalent, and the contents are the same, so they're also equal. So even though the two sets were originally defined in a different way, they actually represented the same set. It's just harder to see it unless we have the set written in roster method. So that's why it's going to be valuable to take a moment and write it out and make the actual list. Now, based on our cardinal number, we can then classify a set as what we call either finite or infinite, and it means exactly what you think it means. Finite means it is a finite set. It terminates, it ends. It means the cardinal number is a finite number. We can actually count the number of items in the set. Now, we have to keep in mind, if you were actually going to count by hand, you may have a really long set, and counting by hand might be unrealistic. So you could have, for instance, 1,000,000 items in the set. But 1,000,000 is still a finite number. Even if you wouldn't want to sit down and actually count out all the elements, you know that you could. If you had enough time, you could actually sit there and you could count out all the elements. Infinite means no matter how much time you have, you could not actually count out every single element in the set. It's an infinite set because its cardinal number is infinite. So let's look at these two sets and let's determine whether or not they are infinite or finite. So in Setbuilder notation, A is all x such that x is a natural number and x is less than 100, strictly less than 100. So we're looking at natural numbers, 1, 2, 3, 4, 5, so on and so forth, but we only want numbers that are less than 100. That is going to be a finite set. If we were to make a list of that, actually write out the roster method, 1, 2, 3, ... and then it would end at 99. 99 would be the largest number. So because that set does terminate, there is truly a place where it starts and a place where it ends. It is a finite set, and in this case, we can say the cardinal number would be 99. There would be 99 elements in that set. Now, what if we do just a little change, only one thing changed? All x such that x is a natural number and x is greater than 100. So instead of less than, now we have greater than. Now we're still only looking at natural numbers, so we're still only looking at counting numbers, but now we want numbers that are greater than 100. So where would that start? Well, it doesn't start at 100 because we're not allowing equality. That means it's going to have to start at 101 since we're looking at counting numbers. So greater than 100 is 101, 102, 103, 104, 105. Where does it stop? Well, trick question. It doesn't stop, right? It keeps going. Any number that's greater than 100, which includes 101 and then onward, would be contained in this set. So this set is never going to end. You could keep listing out things in this set for the rest of your life, and you'd still be listing by the time you die. So that means this is going to be an infinite set. We would say the cardinal number is infinity. We can't actually find a fixed cardinal number, so that's going to be an infinite set. Now, notice that the natural numbers themselves, that's going to be an infinite set. It's infinitely long. We could take the whole thing, we could list out as much as we can, we'd still never finish. So typically when we talk about natural numbers, we're going to talk about smaller sets within the natural numbers, kind of like the ones we've defined here using Setbuilder notation. So all of this terminology, all of this notation that we've developed in this section, we're going to continue to use. So next section, we're going to talk about subsets, those couple little notations we looked at where it seemed like something was true, but it was actually false. We're going to investigate those situations a little further. And then again, we'll look at sets in context, continuing to use this notation, all these ideas.